Today, we're going to make another dent in the universe by running through the first quiz in our second UDEMY course, which is entitled Physics of Astronomy, Orbital Motion, and Kepler's Laws. Now, throughout that course, I make the following assertion multiple times. I say that perspective fries your once weighty eyes, and it gives you wings. In other words, depending upon how you perceive the world around you, how you observe the motion of a system, that's going to either drive your analysis forward, make it more effective and efficient, or it's going to hold you back, make your life harder when you're trying to do that analysis, okay? So in terms of central force problems, what we're gonna find in this particular quiz, which I think is an excellent example, which drives this point forward, is that depending upon our perspective, depending upon what coordinate systems or generalized coordinates we select, that can either make our life easier or can make it harder. So I'm going to show you how choosing the center of mass and the relative motion of our system in this central force problem is going to make our life easier and drive the analysis forward. In the end, we're going to find that we can reduce 3 coordinates down to a 1 coordinate problem, having just one variable, basically paying attention to the phenomenon that is of interest, the central motion, okay? That's gonna be the only coordinate we're gonna deal with, okay? So, before we jump into the video, if you have not done so already, make sure you smash that like button, subscribe to our channel, and hit that notification bell so you can get notified of new problems and new videos that are posted very regularly. Okay, without further ado, let's jump into the problem right now. All right, so in any central force problem, what exactly is going on? In essence, what we have is we have 2 particles where some kind of force is trying to pull them together, but then push them apart. Okay, so this can occur with multiple instances or situations, right? We can have orbital motion, which is the case in my second course, where the force is gravity, where that gravity gets small when they're far away, but when they get closer, it starts to build up and up and up. We can have this in electrostatics, where you have sort of like an electric field that is imparting that force. Or in the problem we're going to work on today, to simplify it, is you can have some kind of spring force that wants to pull those particles closer together. So as the name implies, right, we usually define what's happening through the name. Central force problems are about a force that wants to pull particles back to the center, and that is what induces the motion. So let's jump into the problem statement and let's get started with this problem. So the problem statement is as follows. It states that 2 particles of masses m1 and m2 are connected by a massless spring of natural length L and spring constant K. The spring, much like gravity in orbital motion, as I was just talking about, provides the central force allowing the 2 particles to interact with one another. Assume that initially, particle 2 is resting on a flat surface, while particle 1 is held above particle 2 by a length L. Then, at a time t equals 0, particle 1 is projected vertically upward with an initial velocity v0. In other words, somebody is going to throw this up with an initial velocity, this contraption, whatever it is. The problem states, determine each particle's position at any time t. In other words, we want to solve the equation of motion. So what I have done is I've drawn up this problem right here. What we have, basically 2 particles. We have particle 1, which is farther away from the origin, and particle 2 right down here. Each has a mass, m1, m2. And we're going to track the positions of these guys as follows. The position of particle 1 is going to be y1. I have a little typo right here. This is going to be y1 right down there. And for particle 2, it's just going to be y2. Okay? So we also have a spring that's connecting these guys. And that spring is what is going to produce the force that pushes them together. This is going to be defined by Hooke's law, which is negative kx. So the more you expand it, the more it sort of wants to pull this guy together. Kx is going to be the delta between the 2. And that's that. So the first thing you want to do in any kind of central force problem, you could write out the problem in terms of y1 and y2, and maybe you have another coordinate, or maybe you have 3 coordinates for each particle. That can get quite convoluted. But the point I want to stress in this problem is that we can make it easier. We can use different coordinate systems, right? Perspective fries your once weighty eyes, and it gives you wings to drive our analysis forward, right? We can do that. So the first thing we're going to do, and I'm going to make a little bullet point here, is we want to Let's define coordinate. Let's redefine our y1 and y2 in terms of new coordinates. Okay, so what exactly are those new coordinates? Well, that's what we're going to work through right now. So, what you've probably seen in a Physics 101 course is that you can track the center of motion. We usually call that a big R, okay? And the big R is basically just an average, a mass-weighted average of the positions of these particles. So what we could do is we could define this as m1, y1, plus m2, y2, over the total mass. We're going to call that total mass big M. That's just m1 plus m2, okay? So this can keep track of the center of motion, center of mass of these guys, okay? And the other coordinate we want to use is the relative motion, right? We're really interested in the relative motion that is induced by these central forces. So what we're going to define is, we're going to find a little r coordinate, r, and I guess these are technically vectors, so if you want, you could put little vector notations up here. In this problem, motion is going to be restricted to the y-axis, so you can sort of drop those guys. But I'm going to put those vector notations right there. And we're going to define r as the relative motion between these two particles. So I'm going to define that as y1 minus y2. So that's always going to give us this distance right here between these guys, basically the distance of the spring in between them. So when we have these guys, what you want to do is you want to try and redefine y1 and y2 in terms of big R and little r. In other words, we're going to map these coordinates into different coordinates. We're going to figure out how to define them using our coordinates of interest, big R and little r, right? That's the beginning of any Lagrangian-based problem, okay? So what we're going to do is I'm going to say y1, I'm going to use this guy first. I'm going to say y1 is equal to little r, and I'm going to drop the vector notation because we're acting in the y-axis. It's going to equal r plus y2, okay? So then we could take this guy, we can throw it into our big R right here, and what we end up with is big R is equal to m1 times the quantity r plus y2, basically substituting in and chugging along, baby, plus m2 y2. And all that's left really, after this is divided by a big M, is just to organize. So we want to bring everything on one side, okay? So we can get big M R, or do we want to do that? Yeah, we're going to get big M R, or rather, I'm not going to do that. I'm going to get big R, and I'm going to pull over the little r right here. So I'm going to get big R minus m1 little r over big M. And I'm going to try and isolate my y2 because that's what we want to solve for. We want to solve for y1 and y2, remember? So when we do that, we get m1 y2 plus m2 y2. We can bring those guys out in the front. And all that is divided by big M. Well, previously we defined a big M as M1 plus M2. So what we can really do is we can say, okay, this cancels with this. And in the end, we find that Y2 is equal to big R minus M1 R over big M. And that, ladies and gentlemen, that is the first dent we made in the universe. So we are going to highlight this result in our beautiful galaxy ink. And then we're going to bring it down here. Okay, so now that we have this Y2 defined, all that's left is we need to define Y1 in terms of little r and big R in order to complete that map, that transition over to these new, more efficient coordinates. So what we're going to do is we could basically take this guy and plug and chug. So we know that R, again, R is equal to y1 minus y2. So I'm going to put in the result we just generated, which is minus big R minus M1 R over big M. Okay? And all we need to do is we need to just basically isolate this y1. So we get y1 is equal to little r plus big R minus M1 little r over big M. Okay, so now we just need to combine these terms. So I'm going to leave the big R out front, and then we get plus 1 minus M1 over big M, all times little r. So we know that big M is M1 plus M2, so we can redefine this 1 as M1 plus M2 over M1 plus M2, okay? And when we do that, we're going to have M1 cancel with this M1, and what we end up with is Y1 is equal to big R plus M2 R, little r, over big M. And if I back up a little bit, all I did, again, M1 plus M2, divide by M1 plus M2, M1 minus M1, and then we have an M2 left, and that's where that guy goes there. So we're making a bigger dent in the universe. We're going to highlight that baby in Galaxy Ink. Okay? And this is the map that we're going to use for translating from our Cartesian-based coordinate system into this more efficient system where we're using these alternate coordinates to sort of drive our analysis forward. Next, we want to use the same kind of methodology which always guides us through in the Lagrangea Mechanics problems. In other words, what we're going to do is we're going to derive an expression for the Lagrangian L, which is equal to T minus U. Now, usually we begin this by taking a look at the kinetic energy T, which I've defined here. So the kinetic energy is generally just 1/2 mv squared, and we're going to have to apply it to both of the particles. So in the end, we get a T expression, which is equal to 1/2 m1 times y1 dot squared plus 1/2 times m2 times y dot squared. Now, since we want the generalized coordinates of the center of mass and the relative motion, these two are vectors, what we're going to do is we're going to substitute in these expressions, these maps. We're going to utilize these maps we just derived in order to get those generalized coordinates popping out in our expressions, okay? So we're going to do that by substituting in y1 and y2 right there. So what happens is we get T equal to 1/2 times m1, and then our y1 term, right? If we take the derivative of y1, we know that r is a function of t, little r is a function of t. These guys just become derivatives. So in essence, what we end up with is the following. We get the big R dot plus m2 little r dot over our big M. All that is squared plus 1/2 m2. And then what is y2? Y2 is over here, so we get a big R dot minus M1 R dot over big M. That quantity is squared. Okay, so chugging along, we're going to get sort of a nasty expression, but we don't have to deal with vector quantities. So there's a plus side to doing this using the Lagrangea Mechanics method. Chugging forward, we get a 1/2 m1 big R dot squared plus 2 m2 little r dot big R dot over big M plus m2 squared, little r dot squared over big M squared. And then we do the same thing for this second expression right up here. So we get a plus 1/2 m2. We get a big R dot squared. And as we run through this, you should see similar quantities like the R's and these middle terms. But going back to the problem, we get big R dot squared minus 2 m1 R dot big R dot over big M, and then plus m1 squared little r dot squared over big M squared, okay? So, in order to proceed, we got this huge monstrosity here. What we want to do is we're going to want to try and group terms, okay? We're going to want this big R term here. We see that they have a common term, sort of common terms out front. So what we could do is we can group that into 1/2 m1 plus m2, which is big M, 1/2 big M R dot squared. And then we pay attention to this middle term. So they look sort of similar, except this has m2 and this has m1. Fortunately, we have the cross terms out in front. So in essence, what we get is m1, m2, little r dot, big R dot over m, minus the halves cancel out with the 2's, m1, m2, little r dot, big R dot over big M. So in essence, these guys are going to cancel. These guys just cancel out, okay? Which makes our life easier, okay? And then we have these middle terms. So I'm going to write this out. I'm going to write it out. So we get a plus 1/2 m1 m2 squared little r dot squared over big M squared. And then we get another 1/2 m1 squared m2 little r dot squared. All that is over our big M squared. So we're making headway, but right, it would be nice if we could group this little r dot squared, okay? It would be nice. So what we're going to do is we're going to see that it's sort of like m1, m2. So I'll write it out for you guys. So this becomes 1/2 big M R dot squared. But as I was saying, we have an extra m2 here, and we have an extra m1. But aside from that, we have common terms. So what we get is we can pull out this common term, and we see we have m2 plus m1. I'll write it as m1 plus m2. And all this is multiplied by m1, m2, little r dot squared over big M squared. Okay? So when we look at this is no different than, this is just big M, right? So cancel that guy out with this. We get a little m there. And in the end, what we find is that we just have t equal to 1/2 big M R dot squared plus, we're going to use a term called mu little r dot squared. Okay, so this is a big result, right? We're halfway there to getting our Lagrangian. So I'm going to highlight this baby in our beautiful Galaxy ink. Okay, so we got this guy, and in essence, this is just m1, m2 over m1 plus m2. So this is a common term you usually find when you're dealing with gravitation and things of that nature, a lot of central force problems. In essence, what it's saying is that, let's say m1 is much less than m2. Okay, in that case, mu is very close to m1. So the case which that happens is with the sun and and the Earth, right? So if you have the Earth is much less than the sun. So in essence, I guess I'll write it out so you guys can see M1, M2 over M1 plus M2. If the Earth is M1 and it's much smaller than M2, this guy down here is approximately M2, so it's like approximately M1, and let me just make sure I'm not writing over my face. No, I'm not. So this is M1, M2 over M2. And in essence, what happens is this guy cancels out, and it's approximately equal to M1. So this is the kind of terminal or the general thinking you have with reduced masses. That's what this mu is. It's a reduced mass. But it's usually used when you're dealing with central force motion, okay? So we got this guy, and as you can tell already, it sort of seems like it's getting separated into terms of the center of mass coordinate and our relative motion coordinate. Let's chug along. Let's proceed. So next, to complete our expression for the Lagrangian, what we need to do is we need to calculate our potential energy U. So that potential energy U is going to be defined in terms of two components. It's going to be in terms of the gravitation we're working against and also the potential energy that is stored within this spring. Okay, so with the potential energy due to gravity, we're going to have a reference. Our reference is here. And what we usually say is that the potential energy is basically the negative integral of our F, our force, dotted into the distance we're going. So in this case, everything is moved up. We got, let's say we got a particle right here. It has some kind of force going down. We'll call that Fg. And in essence, we moved up. We moved up. We moved this guy up. So we moved it up. We're putting energy into this system. So when we evaluate this guy, Fg.dr, this angle between these guys is 180 degrees. Cosine of 180, this is going to give us a, I guess I'll write it out. I'll write it out for you guys. So you've probably seen this already in my course, but if not, just to make it clear, so we get a force. We'll call this our force G. We get the magnitude. We get the magnitude of the distance that we traveled and the cosine of the angle between these guys, which is 180. So in this case, this becomes -1, and the negative is going to cancel out with that guy. In essence, we're just going to get the force G, our magnitude of the force as such, times dr, and it's going to be positive. So both of these guys, as long as they stay above the origin, which is true because they cannot go under the ground, we're going to have a positive potential energy for these guys, okay? So backtracking, getting rid of this, now that you guys have a better understanding of that, we're going to come up here, and we're going to take care of those gravitation terms after I get rid of this little dot right here. And what we're going to say is, we get our black ink, we're going to say that for particle 2 and 1, we're just going to get M1 G Y1 plus M2 G Y2, basically the force times the distance it was moved up, the energy added into our system, right? We have the potential to do work because of raising this guy above the ground. So we got these guys, and then all that's left is just our the potential energy we get from our spring. Now, if you've taken Physics 101, we know that's 1/2 K times delta X. So that's delta X is the hard part here. So I'm going to write this out, and we're going to talk more about that in a second. So this is just 1/2 times our spring constant K, and this is derived from Hooke's law. So we get K times our delta X. So delta X, we know that this has a natural length of L. So if the distance between these guys is just defined by our central force coordinate R, and this is where this designation becomes useful, R is just y1 minus y2, which is that distance. So this becomes larger than L. We're going to have that central force come into play to try and pull these particles together. So the way in which we want to define this is in terms of R minus L. And You can define it as the opposite L minus R because we're squaring it, so the sign doesn't matter. But we just want this delta, basically the delta between these guys. So this is sort of like our delta X we got going on right here. And we define it as such. So all that's left really is to substitute these guys, use our trusty map to transition over to our new generalized coordinates, and then we can plug this guy in for a Lagrangian, okay? So let's do that just right now. So we get this equal to M1G. Well, what's Y1? Y1 is this guy, so it's a big R plus M2 little r over big M. And then we do the same thing for particle 2. So that's M2G. Y2 is just big R minus M1R over big M. And then our spring potential energy just comes along for the ride. So that's 1/2 K little r minus big L squared. Okay, so we got a lot of terms here. What we need to do is we need to try to group them. So what we're going to do is we're going to say M1G big R. We have that over there. We have M2G big R. So we want to group these guys. We basically get M1 plus M2G big R. And we know that M1 plus M2 is our big M. So we're going to define this as our center of mass Mg big R. And then we want to see what we can do with these guys. Well, we see that they're pretty similar. So we get M1, M2, GR over M. This is going to be minus M1, M2, GR over big M. So in essence, we see that these guys, fortunately, they cancel out with each other. So that makes our life super simple. So we just get this term here, and then we get a plus 1/2 K little r minus L squared. And that is our potential energy. So we made another dent in the universe. Our dent is getting bigger. It's getting more distinguished. We're getting a grip of what's going to happen with this system, this phenomenon. So I'm going to highlight this in our beautiful Galaxy ink. Bam, we're making progress. So we got that result. Next, what we want to do is, again, we're trying to find the Lagrangian. We've got all the puzzle pieces. Let's fit them together and see the full picture. All right, so let's do just that. We've got our puzzle pieces right here. We got the kinetic energy, the potential energy U that we just derived. Let's put them into the formula we know. The Lagrangian is T minus U. So when we do that, we end up with the Lagrangian is equal to 1/2 big M r dot squared plus mu little r dot squared. So that's our T. And then we subtract mg big R minus 1/2 K little r minus L squared. So that's the final expression we get. I'm going to rearrange it a little bit and talk about why this result is important for central force problems and also for the analysis that is outlined in my second course. So what we're going to do is we're going to group terms. So we're going to get a 1/2 big M big R dot squared minus big M G big R. And then we're going to get a plus mu r dot squared minus 1/2 K quantity R minus L squared. Okay, so what I'm going to do is I'm going to say, well, I'm going to write our Lagrangian first in here. This is the Lagrangian we get, but there are some very important implications associated with this. So what I'm going to highlight is first over here, highlight two portions of this guy and show you what we've just discovered. So we discovered by changing our perspective, by looking at the motion in a different manner, what we found is that we broke the Lagrangian up into separate parts. So this, we see that the Lagrangian of the center of mass term is right there. And that is added with a Lagrangian related to the relative motion. So in essence, it's sort of like we're analyzing the problem as if we took all the mass here, placed it at the center of mass point, and observed that motion, right? This is just 1/2 mv squared minus mgr. This is the Lagrangian at the center of mass. And here we took another particle of mass mu, reduced mass. We took this reduced mass here and we observed the motion, the relative motion. So obviously that's 1/2. I actually missed a term here. I forgot to carry this through. So this should be a 1/2 right up here. Apologize for that. Let's put that in. But anyway, it's our kinetic energy 1/2 mu r dot squared. And we're subtracting our potential energy that's associated with the relative motion. So that's an important implication. And as we run through this problem, our generalized coordinates, right, we're going to have two generalized equations, one for the center of mass motion and one for the relative mass motion. So we sort of decoupled that phenomenon. And we're going to see that one of these coordinates in special situations, especially in the analysis in our course, is going to be ignorable, right? So if we switch to that center of mass reference frame, we're going to find that we get only one particle, basically, of mass mu that we have to take a look at. So we reduce our problem down from a ton of different coordinates. We can have 3 coordinates here, 3 coordinates here. That's about 6 coordinates down to a system of 1 coordinate that drastically simplifies our life, that drastically simplifies our problem, and really makes our analysis efficient and effective. Okay? So next, what we're going to do is we're going to take this Lagrangian we've just derived, and then we're going to work through the different Lagrange's equations we're going to have for each generalized coordinate. Okay, so the first generalized coordinate we're going to work with is the center of mass coordinate, big R. And all we want to do is the same thing we've been doing so many times with these Lagrangea Mechanics analyses. We take our Euler-Lagrange equation, which is basically the second partial of the Lagrangian with our coordinate delta R, and that is equal to the derivative with respect to time of the partial, the Lagrangian, with respect to the velocity of our coordinate. So this big R dot. And then we just plug and chug. So when we do this, what we find is we come over here. So we're looking for little r. So basically, that's just the only term we have is this guy right here. So that's just the derivative of that is negative big M G. And that is going to be equal to the derivative with respect to time of this Lagrangian. So we need to find where big R dot is located. That's only in this term right here. When we take the derivative, that 2 comes down and cancels out the 1/2, and we get basically an M R dot. So we solve this guy, and that ends up with, we get a negative mg equal to m big R double dot. Now, if we take a look at the different terms that are associated with this, we have something over here. This is the force, basically the force of gravity of the entire system. And what we have on the right here, this is basically our MA. This is the MA term in Newton's second law. So basically all this is saying is that in the center of mass frame, any force acting upon this is going to impart some kind of acceleration to that system that's going to move it. Okay? So, in other words, if we have a system with no external force, which you see in my second course, you're going to get something like this. You're going to get something that looks like R double dot basically equals 0, which means that your velocity, R dot, is a constant. So that says that the center of mass of the system is going to move at a constant velocity. And for this reason, I say that that makes this coordinate ignorable. So in any central force problem, when you end up with this, when you have no external force, the center of mass coordinate is ignorable. In other words, right, this doesn't posit any kind of information that can allow you to further understand the motion. It's just going to move at a constant velocity. Okay, so what usually happens is you can change your perspective, right? Perspective provides you once weighty eyes and it gives you wings. You can change your perspective such that you move with your center of mass so that this guy, R is 0, right? Because when you move with the center of mass, when you calculate this guy, it's going to become 0, right? Because from your tangent point, it's like right on you. It's not moving. So its location from your perspective is 0. So when you do that and you move with that center of mass reference frame, this coordinate is useless, and really the analysis comes down to only one single coordinate, which is your relative motion, basically this guy right here. So this becomes the only coordinate, and that's why I said in central force problems, by taking this an analytical approach, by changing your perspective, you can reduce the problem down to one coordinate, basically a one coordinate problem, the little r, and you're basically analyzing one particle, mu, with a mass mu, that only has relative motion, which is a much simpler problem to analyze and something that we definitely will take advantage of throughout the course, throughout this second course we've put together. But in this case, we have an external force, this gravity mg. So it's going to be simple, but it's not going to be as simple as I just described. But I think it was important to show the power of this approach in any kind of central force problem. And this applies whether it's gravitation, electrostatics, spring force, you name it. You name it, okay? So coming back to the problem at hand, what we want to do is we want to actually solve this problem. So what I'm going to do is I'm going to simplify this. This is basically, we're going to cancel off these big M's. We're going to cancel that guy with that guy. And now it just becomes a very easy differential equation. We need to integrate this 2 times. So first, we integrate it once. If I get my black ink out right here, we get r dot is equal to negative gt plus a constant c1. Then we have to integrate it again, and we end up with the equation r sub t is equal to negative 1/2 g t squared. Again, I'm just integrating the right side again, plus c1 t plus c2. Okay, so that's an important result. That is the result for keeping track of our center of mass. So I am going to highlight this baby in our Galaxy ink because we're making another dent in the universe. We're doing a really good job here, guys. Good job. So that's the guy we get. And it's pretty, right, this is straightforward. This is like kinematics 101. Like this is our initial velocity v0 we're going to find probably. And this is just some coordinate, some constant that's probably going to be the initial position of this guy. So this is the equation we're going to use that we're going to have to solve using our boundary conditions later on. Next, let's jump into the most important coordinate that's going to give us the most information about our relative motion. It's our relative motion coordinate, little r. Okay, so working now with our center of mass coordinate, with this generalized coordinate, we get the following Euler-Lagrange equation, which we're going to use to solve for this equation of motion. So it is the partial of the Lagrangian with respect to our path variable, which is r in this case, our generalized coordinate. This is all equal to, again, the normal derivative with respect to t of the partial of the Lagrangian with respect to the velocity of our generalized coordinate. And that is the recipe we're going to use for deriving our equation of motion. So we take this guy and look at our Lagrangian. We come up here. On the left side, we see that we only have a r term right here. So what we want to do is we want to differentiate that. And what we end up with is we get a negative k r minus l. That's what we get on the left side. And on the right side, we're going to get this d dt. And now we got to find portions in here with our little r dot term. That's only this term right here. So when we differentiate this, again, the 2 pops down. We get a mu r dot And simplifying this, we get a negative k r minus L. And all that is equal to mu r double dot. So in essence, again, it's like we have a particle of mass mu. This is our MA term. I'll write down the two different components we have here. This is our MA term from Newton's second law. And this is our force. This is our Hooke's law force, right? This is the spring force. I'll call it Fk. Just trying to restore it. And this negative term here is because the R term is getting smaller. The force is acting to push these guys together. So this describes all the motion we would have for the center of mass, or rather the relative motion reference frame. Okay, so we got this guy, and all we need to do now is solve this. So I've moved the equation of motion up here and just brought the mass down over here, which will make it easier shortly. But to solve this is a little bit more difficult than what we had down here with the center of mass coordinate, big R. And the reason why is because when you try to differentiate this, like it's just not going to work. So what I've said previously in a lot of videos in which we solve differential equations is that solving differential equations is like erecting a building. What you need to do is you need to put up sort of scaffolding of what it generally looks like, and then you fill in the little details, okay? So we know from solving ordinary differential equations that the solution of this is basically, it's going to have two components. The solution is going to have a component due to this R, and it's going to have a component due to this constant L. So when you differentiate something twice and you get the same result plus a constant out front, that suggests that the solution is going to be in terms of an exponential E. Okay, so we're going to pay attention first to that exponential part, and then we'll consider the constant part. So what we're going to assert is we're going to assert that the solution R sub t is going to have first a transitory solution, plus a stationary solution. Okay, and in the equation of motion, the stationary term is going to be described by this constant. And the transitory, which is like transitioning to a different solution, is described by this. That's usually driven by some kind of force. In this case, it's going to be the negative k times r, this spring force. And we're going to say the transitory term is going to be defined in terms of RT is equal to, this is basically erecting our scaffold, AE to some constant lambda t. And then we're going to have to add on the stationary part, which I'm going to call RS. This is going to be in terms of a constant, which I'm just going to call, let's call it big B. Okay, so all these guys get added together, and that gives our final solution after we account for superposition. Okay, so looking at the part when you're driving the system with some kind of spring force, when it's starting to move, trying to get to steady state, we're going to have this guy. We're going to assume that solution. We're going to plug it in, and we're going to see what happens. So basically, you get negative k over mu a e to the lambda t. And I'm going to drop out this part here, the L term. And I'll show you why once we get the final solutions. And that is equal to a lambda squared. Basically, I'm differentiating this guy twice. A lambda squared, e to the lambda t. And you've probably done this many times. I'm getting the characteristic equation, but I'm doing it so you guys can see all the details. So we cancel out all the common terms here. Get this guy. And the characteristic equation just tells us that lambda squared is equal to negative k over mu. Which tells us that we have imaginary lambdas, which tells us that what? Wait for it, that it's oscillatory behavior. So our lambda, and I'll tell you why in a second, our lambda is going to be equal to positive or negative k over mu I. So when we have this I time, e to the it, right, we use the Euler identity that gives us cosines and sines. And if we want to use superposition, what we have to say is that the final solution for this guy is r little t, our transitory part. This is equal to, we're going to call it, let's call it C3 cosine root k over mu t plus C4. And again, I'm assuming you guys have seen this before, so I'm not going to write out the Euler identity. Root k over mu. And I'm going to check if my face is not blocking this off. T as such. And all that's left now is really to find a solution for our constant part, the transitory when it's in steady state, basically accounting for this L term here. And what we know is that if we take this guy and differentiate it twice, if we differentiate this guy twice, what's going to happen is it's just going to cancel out. So if r is equal to b, this guy's going to cancel out. And we're just going to get, we just get negative k over mu b minus L equal to 0. So this basically tells us that b is equal to L. I'm probably writing on my face. No, I'm not. We're good. And this gets us the result that Rs sub t is equal to b. So we got these two equations here. Or let's back up. This is actually L because we saw for b. That's L. And then we want to make board space. So I stated I would show you guys how these guys actually get implemented into here and we don't lose any information. Well, if we split it up as such, if we take double dot of RT and RS is a constant, that becomes 0. So this just becomes, if I get a black pen out here, this just becomes RT double dot. It's equal to negative k over mu. So this is basically just our RT plus RS minus L. So when we work through all this, you could plug it in and you'll see that both sides are equal. But in essence, what we can say is that this is no different than this side here, and it's equal to R double dot, and we get the same thing, okay? So all that's left is to write out the general form of this equation that we've gotten. That basically we're taking the map, our equation of motion, and we're showing what clues it provided us with. So the map basically dictates that this center of motion is described by the equation R sub t is equal to C3. We back up. We want that C3 cosine of root k over mu times t plus C4 sine of root k over mu times t plus L. Okay, so that is the general form. Okay, what we need to do, we want to highlight this baby because that is super, super freaking important. We made a dent in the universe. We're almost to our final solution. We've almost solved the problem fully. Next, what we need to do is we need to apply our boundary conditions to get the final solutions. All right, so at this point, we've pretty much built up the building of our motion or the r sub t and little r sub t. Now we need to fill in the little details like the piping, maybe there's a garden, so on and so forth, in order to get the final picture, okay? So that involves defining the details regarding C1, C2, 3, and 4. In essence, we want this model to converge upon reality, the situation that we are analyzing, right? So in order to do that, what we need to do is we need to use the initial conditions and the boundary conditions that are given to us in the initial problem. So in the problem, it states that y1, particle 1, was initially thrown up with a velocity v0. So y1 dot at 0 must equal v0. This is number 3. This is where I got this guy. Furthermore, if it takes a while for that motion to be transferred to particle 2, we know that the velocity of y2 must be 0 right when we start from rest, right? Because this is initially v0. It takes a while for that to move and the spring to react to pull that bottom particle. So what we do is we set the velocity of particle 2, y2 naught, equal to 0, okay? So we got the velocity initial conditions done. Next, we could take a look at the positions. So for particle 1, initially, or rather particle 2, the problem says that initially, let's see, particle 2 is resting on a flat surface. So the flat surface is at the origin down here, which we're going to set to y equals 0. So for particle 2, y2 at 0 equals 0. And if this guy is initially at a length L, the natural length, that means that particle 1 must be equal to L. So y1 naught must equal to L. So you're probably thinking, well, what the hell am I supposed to do with this? Our equation in terms of big R and little r. What we're going to do is we're going to translate this over using our map, our handy dandy map. We're going to translate this over to our new coordinates. So what we're going to do is first, for the first condition, number 1, y1 naught is equal to L. Okay, so y1, this guy is equal to L. y2 naught is equal to 0. So this is going to be sort of like 1 and 2. So let's see. Yes, this is going to be 1 and 2. So that tells us that if this is L and y2 naught is 0, then r naught, and again, I'm using this guy right down here, y2 is 0, y1 is equal to L. This must be m1 L over big M. Okay, so we get that guy. Next, we're going to take a look at this guy right here. So what we could do is we could use the same thing. So that's going to give us, okay, y1 is equal to L. And so that means that r sub naught is equal to big L, right? So in essence, all I did is I plugged these guys in right down here. y1 is equal to L, y2 is equal to 0. Little r must equal L. So that takes care of 1 and 2. So next we got to apply 3 and 4. So when we do that, we find that little r dot is equal to y1 dot minus y2 dot. So y2 dot is 0. So basically 3 and 4 give us the fact that, so y1 dot is going to be v naught. So that means that r dot sub naught is going to equal v naught. And that makes sense because when you throw this up, it's increasing by v naught. So that better increase if particle 2 is stationary. Similarly, this makes sense also because initially this is a length L. So it better be that relative motion between them, or relative position, better be L. So next, all we need is big R. So big R dot at 0. So all we do is we take these guys. So again, it's just y dot and y1 dot and y2 dot over here for r dot. We're going to have y1 dot is v naught, y2 dot is 0. So again, this is equal to m1 v naught over big M. And what you could have done, you could have converted this over to the y coordinates. I find it easier to do this first, to figure out these constants and then convert, which we'll do shortly. But using these initial conditions, next what we want to do is we want to apply them to both these guys and try to eliminate these constants. So first, what I'm going to do, I'm going to use this guy right here, and I'm going to say that R naught, which equals L, is equal to C3. Well, this cosine of 0 is 1, sine of 0 is 0, so C4 cancels out, so it's going to be C3 plus L. And this allows us to assert that C3 is equal to 0, which is a big, big result. So we're going to highlight that guy. That's our first result we've obtained. Next, I'm going to tackle the next easy one, which is this guy, the big R sub naught. So if I get my black ink, big R sub naught, which is equal to M1L over big M. That is just equal to, well, we're going to get 0 right here. We're going to get 0 right here. We're going to get C2. And C2 is just equal to that. So these first two ones were pretty easy. And in general, it's best to start with the non-derivative ones just because it's straightforward. So we're going to highlight that in our Galaxy ink and then make some board space. Okay, chugging along. Next, we want to tackle the derivatives, but in order to do so, we need to take the derivatives of these guys. So we're going to start by saying that R dot is equal to, we found C3 is nothing, so we get a C4. The derivative of sine is our cosine, and this guy pops out. K over mu. We're going to get cosine K over mu t. And then we have to add an L. So when we consider the point when t is equal to 0, what we end up with is a V naught. A V naught is equal to, again, 0 in for cosine. Cosine 0 is 1. This is going to be C4 times root K over mu, our omega in essence, our frequency. So when we solve that guy, we get C4 is equal to V naught over root K over mu. Okay? So we're going to highlight this guy. And again, this is sort of a laborious process, but if you keep chugging along and you keep yourself organized, you can end up with the correct result, which we will do. We got this, guys. Okay, so let's make board space. So last but not least is the center of mass term, the big R right here. And we're going to do the same thing we just did previously by taking the derivative and then evaluating. So R dot is equal to negative GT plus C1. So we got the only constant that we haven't solved for. And then we want to just plug and chug. So R dot is when t is equal to 0 is equal to M1 V naught over big M. And this guy's going to cancel, so we get C1 pretty easily. So these are all the details we were trying to find for filling in our buildings or finishing our equation. So we're going to highlight that in our beautiful Galaxy ink. And then what we want to do is we want to plug these guys in to get the final solution to see the big picture. And then we're going to use this to translate back into our Cartesian coordinate system. So doing just that, now that we have the extra board space, we get little r sub t, using this as reference, equal to, okay, we need C3. C3 cancels out. So I'm going to come in here. This guy is going to be 0. We have, no, we don't have any other zeros. So that guy's 0. We just have C4, which is V naught over this guy here. I'm going to use shorthand. I'm going to call it omega, and you're going to see why. Omega times sine omega t. So in essence, I know this is a frequency, so I'm going to redefine this guy as the frequency to make our lives easier when we solve this. And that is all added by a length L. So this guy got simplified quite a lot. Next, what we want to do is we want to do that with the center of mass coordinate right here, the big R sub t. And what we have is negative 1/2 g t squared plus c1 times t. Well, that's just m1 v naught. m1 v naught over big M times t plus c2. So we define c2 right here. That's plus m1 L over big M. All right. So next what we're going to do is we're going to want to take this and our map right here. And we're going to use that to finalize the problem. Normally in analysis, you would not have to go back to Cartesian coordinates, but as a general exercise for this quiz, I've had students try to convert back just to get practice with using these coordinates. So let's do that next. All right, so the method of going from our generalized coordinates back to Cartesian coordinates is a little intense. It's a lot of math, so we're going to want to make sure we keep ourselves organized and stay on track. Okay, so the way in which we're going to do this is we're going to basically just use this map. So this is going to translate our solution into the Cartesian solution. What we're going to do first is we're going to take this guy and we're going to basically throw in the R in terms of here. So if we isolate y1, we get y1 is equal to R plus y2. And then we can pull this guy in, which is just V naught over omega sine omega t plus L plus y2. So we have two unknowns, and we want to get just one unknown that we can isolate. So now what we want to do is we want to use the other component of our map that we have, which is this big R here. And we don't really want to throw these guys in yet because we won't get the right result we want. What we want to do is we want to throw this, our result here, into here to aid the translation, to aid our map, our tool. So what we do is we're going to find that we have minus 1/2 g t squared plus m1 v naught over big M t plus m1 big L over big M. All this is equal to what our map tells it. So that is m1 y1 plus m2 y2. And I know, hang in there, it's a lot of math, divided by big M. And what we need to do is we need to isolate an expression for y2 in terms of all these parameters and y1, and then we'll substitute it back right into there. So what we're going to do first is we're going to multiply by big M, we'll subtract the y1, and then we'll divide by little m2. So what we end up with is negative 1/2 big M g t squared plus m1 v naught t plus m1 L. And all that is equal to m1 y plus y1 plus m2 y2. All right, I'm just going to check. Not writing over my face, all is good. Next, what we want to do, we want to bring this guy over and then divide by m2. So when we do that, we get negative 1/2 big M, big M g over m2. And I'm doing two steps in one here, times t squared plus m1 v naught over m2 t plus m1 over m2 L minus m1 over m2 y1. All that is equal to y2. So for the interest of space, what we're going to do is I'm going to just bring this up here and erase everything below here. It's getting a little messy here, but we'll make do. So we get this guy plus L, and then we're going to get this minus basically just down here, just bringing it straight up here, minus 1/2. Or I guess I can copy and paste, right? Let's do that. And what I'm going to do is I'm going to begin by taking y1 to the left because that's what we really want to solve. And then we're going to simplify. So when I bring that to the left, we get a 1 plus m1 over m2 y1. So if you have 1, that's like m2 over m2 plus m1 over m2, which is no different than basically big M over little m2 times y1. And that is all equal to v0 over omega times sine omega t. We want to group some of these terms. I want to group the L's. So that's going to be L. So it's basically the same thing. It's going to be same thing we got right over here. So it's 1 plus m1 over m2 is equal to m2 over m2 plus m1 over m2. So that's just big M over m2L. Then we have minus 1/2 big mg over m2 t squared. I hope I'm not writing over my face at this point. Nope, works still good. Plus m1 v0. We are running out of space though. It's a big expression over m2 times t. Okay, we're making some headway. Now all we need to do is multiply by little m2 over big M, and we get our final expression. So let's do that. So y1 sub t is equal to v0 m2 over big M omega times sine omega t plus L minus 1/2 gt squared. Basically, these guys cancel out. Plus m1 v0 over big MT. Bam! That's a beautiful result. So we made this the biggest dent in the universe yet. We're going to highlight that in our Galaxy ink to signify that beautiful fact. And there you have it. So this is the result we got. All that's left is we need to find basically y2. So it's going to be a lot of math that still remains. But when we get that, that'll be basically the end of the problem. So let's jump into that last part. Hang with me. It's a lot of math. We're going to get through it. So to get y2, I believe it's easier to achieve that end goal using this guy here and this guy here instead of this big equation. So that's what we're going to do. We're going to plug this into here, plug that into there, use our map, and then use that to fill in these final details that we want. So doing that, pulling this guy straight up here, little r is equal to v0 over omega times sine omega t plus L. That is equal to y1, which is just v0 m2 over big M omega sine omega t plus L minus 1/2 gt squared plus m1 v naught over big M t. And then we have this y2 right here. So we get the minus y2. And the name of the game, after I check if that's cut off, no, we're good. The name of the game is basically, I'm going to take this guy to the left. We're going to take these terms to the right. And then we're going to see what happens. So we're going to get y2 on the left, and then we're going to cancel terms. We're going to cancel this guy and this guy initially because they're going to cancel no matter what. And then we're going to get, okay, so how do we do the sign terms? So that's going to be, well, we're going to group the terms. So initially we have this guy, V naught M2 over big M omega minus V naught over omega, all that times sine omega t minus 1/2 gt squared plus m1 v naught over big M t. All right, and all that's left is really to simplify this. So we can pull out additional terms. So v naught over omega is common. So we're going to get an m2 over big M. I'll sort of do this as an aside. m2 over big M minus 1, because we're pulling out the v naught over omega, so that's what this is equal to. These guys, like that. This has to be equal to, well, we could say that 1 is just big M over big M. So this is going to be M2 minus M1 minus M2. So basically, I'm just saying this guy right here is big M over big M. And I'm grouping the terms. So this becomes big M. And then this guy's going to cancel. That guy's going to cancel. And we just get a negative M1 over big M. Okay, so using that aside and plugging it in, I'll just leave it at the bottom here and then erase it after we've solved it. That basically gets us our final equation. You can rearrange this in better form, but I'm going to leave it as is. So that gives us y2 sub t is equal to negative, what is it, m1 v naught over big M omega sine omega t minus 1/2 gt squared plus m1 v naught big M t. All right, and that is the final equation we get. So that is the biggest dent in the universe we can make with this problem. I'm going to highlight it as such. And that's that. So we've really worked through multiple perspectives on the same problem. We've got the y1 right over here. I ran out of board space, so I sort of put it over there. And we have the y2 down here. They're equations we would expect. They've got signs, they've got t's, t squared, 1/2 gt squared. We're used to that kind of stuff, especially with springs. But we also have the perspective of taking a look at the center of mass as follows and the relative motion r. And the big takeaway we have here is that, again, as I stated multiple times, perspective pries your once weighty eyes and it gives you whoosh, wings. By changing how you look at a problem, by taking a different perspective and seeing how motion unravels in front of you from that different vantage point, that can either drive your analysis forward or hold you back. In this case, we found by looking at the center of mass coordinate and the relative motion coordinate that the center of mass coordinate is, in essence, ignorable. And because of that, if the external forces acting on the system sum up to equal 0, what we can do is we can say that momentum is going to be constant. From conservation of momentum, it means that the system is going to move at a constant velocity, and allows us to ignore that coordinate. In essence, it reduces the problem down from what? If you have two particles, 6 degrees of freedom, down to 1 degree of freedom, the relative motion, and allows us to focus on what we're really interested in, right? Basically, that relative motion due to the central force, okay? So in my course, Physics of Astronomy, Orbital Motion, and Kepler's Laws, this idea it's used prominently, and we use a lot of different techniques to simplify the analysis because the equation of motion can get quite convoluted. But at the end of the day, this really drives the analysis forward. And I hope this problem has highlighted the beauty of this method and the beauty of really changing and looking at things differently and using that to guide what you do and to guide your analysis forward, in essence. Okay, so if you have not done so already, make sure you smash that like button, subscribe to our channel, hit the notification bell, and in doing so, you'll get notified of a ton of nice new videos that are available. If you have a problem you want me to solve, send an email to me at ed@thekaizeneffect.com. I'll solve it for you. Yes, for you for free, no charge. And maybe we'll do a live stream if you're interested in that. Drop a comment in the comment box below. But that is the end of today's video. I hope you enjoyed it. Stay tuned for future videos. Thanks for watching.